Mantel. I am a mechanical engineer at Temple University. Our company is Friendly Aquatic Power, and our project is water energy harvester, optimization of a transverse horizontal axis water turbine with the inclusion of turbines. So, in our abstract, what do we want to do? Our project involves the design, implementation, and optimization of the transverse horizontal axis water turbine. Our turbine is developed to convert kinetic energy as opposed to hydrostatic energy into electricity. The design will focus on optimization of the turbine blades by the inclusion of turbicles on the leading edge. The system will feature a dot for short with a rotor that its rotational axis parallel to the incoming water and transverse as it will be on its side. So here's our team members. My name is Dan again. I am the Senior Design 1 leader, and I'm in charge of documentation, fluid dynamic principles, and various prototyping. This is Alan. He is in charge of the frame prototype, frame design, and various other things. This is Ivor Sesome. He's in charge of our electrical components. And this is Harry. He's in charge of our blade manufacturing. So our primary advisor is Dmitry Weinstein. He has his primary focus, his PhD is in physics from Moscow, I believe. We also have a secondary advisor, Dr. Chen, who has various experience in wind turbines. And we also have some technical advice from Dr. Biswas. So why do we want to do this? First, we want to promote hydrokinetic energy as opposed to hydrostatic energy because it's less detrimental on the environment. Hydrostatic energy usually destroys water life as that fish and other things usually get caught in the turbine versus hydrokinetic. United Nations Millennium Goal, we want to create a system that is environmentally sustainable and has zero emissions. We also want to reduce our dependence on non-renewable energies such as fossil fuels, and the availability of tidal streams and rivers present hydrokinetic energy as a viable renewable energy. So, this is our project. As you can see, our water comes through, it's the turbine, then it goes to three various parts. You have the frame over here with steel support and supporting blades that will hold the motor and the bearings. You have the turbine blades, which is part of the rotor, which have turbicles on the leading edge and a base foil. This base foil is based on an NACA 0012 foil. We also have the electrical system, which includes an induction generator, voltage and RPM sensors, and an AC to DC rectifier. So here's what the actual turbine looks like. As you can see, it's a transverse horizontal axis water turbine. Transverse as in the axis is this way, of rotation is this way, and the water flow goes straight through the turbine, parallel as the blades are. So, what are some constraints? The turbicle blade must reduce stall at a certain angle of the path and improve the efficiency of the turbine. Structural support must be able to withstand various forces underwater. Our electrical generator has to be able to create voltage and power at low RPMs. All electrical components must be waterproof, and maintenance, we must be able to disassemble and reassemble the turbine easily. So some non-functional design constraints. We want to keep costs as low as possible so it can be developed and mass-produced. We want safety no more than 1 meter per second, as that any more than that, it becomes dangerous for us to handle it in water. Environmental, we want to allow fish to be able to swim through it, and it's sufficiently large enough for fish to swim through it. Materials, we want to use materials readily available so it will cut down on costs. And reliability, we do not want to go back into the water to fix the turbine, so we want to prioritize a long life. So, how do we design this? First, we did in SolidWorks. We did some flow simulations. As you can see here, the difference between a regular foil and a turbicle, one with turbicles, is that after the leading edge, there will be vortexes. These vortexes are believed to induce more lift and reduce drag. So, because actual data and hardware testing is better than simulation, we moved to 3D printing the foil and testing it in the wind tunnel, as you can see here. So here are some preliminary results from it. As you can see, we have some increase in lift and decrease in drag. We did further testing here, where you can see the coefficient of performance is higher slightly, but specifically here you can see that the turbical blade continues to, the coefficient continues to rise as the angle of attack rises, versus the regular blade which stalls around the angle of 15 degrees. So moving on to the prototype, we wanted to make 3D molds so we can mass produce the turbical blades very easily. This is one mold that came out that we used polyurethane expanding foam. However, it did not, results weren't consistent, so we moved to another polyurethane resin. As you can see here, we are fiberglassing the blades together. However, at the end result of this, we found that it was much too heavy. So we moved on to a third method, which is 3D printing the blades. It took approximately 120 hours to print 9 blades for our entire turbine. And here they painted temple red. So our assembled turbine looks like this. This is our first prototype before we revised it, and we began to test it. This is our first test at Pennypack Creek, right below Buree Road. Unfortunately, this one did not work. We found that the flow exited around the supporting wooden part, so we had to revise that. So we revised it, and thus this is the prototype we have right now. The flow will not go through this, it will go directly to the rotor. And so we also increased the angle of attack, relative angle of attack, to 20 degrees to experiment if that would help. So some more of this. If you see, the rotor is attached by 2 nuts and 2 washers, as you can see there. Because our shaft was only available in 36 inches long, we had to get 2 of them and attach them in the middle. Here is our motor, and our shaft is a 2-to-1 ratio, as at the rotational speed of the rotor. Produces twice the rotational speed of the generator. So some tests. What we want to find is power efficiency, if it's waterproof, if it works essentially, and if all our initial design constraints are met. So testing, we brought the turbine back to the same area. We put it into the water and tested it again. However, this time we found that the turbine having a high angle of attack would induce stall, so it would not turn. So we moved to a higher place where there would be a higher velocity, more upstream. And then we tested it here again. At the same angle of attack, it continued to stall, so we had to reduce the angle of attack back down to 10. And thus it works with them. And you can see here, the flow velocity is about, we measured it to be about 2 feet per second, a little over 2 feet, and it's rotating at approximately 400 RPM. Alright, so we put data.
The best part was short. It was too short.
How many blades?
3 blades.
3. What did you use to measure the water velocity?
We dropped a floatable object into the water velocity, and then we timed it as it went across 1 meter. 48 inches. That was our yardstick.
You also did RPM.
Yeah. We also used a tachometer to measure the RPM of the rotor.
Great.
Alright. So then since we know it now works and we acquire data, we move downstream where it is deeper and the velocity is slightly less. So our test data summary as results. At upstream, we had a water velocity of just over 2. We produced 6.63 watts. This didn't take into account how much we lost through the rectifier and the efficiency of the motor. At trial 4, we moved downstream where the water velocity was less and we got about 3 watts. So that is an analysis, what's out there. We designed specifically for streams with aquatic life. So basically, we can put it almost in any stream without it affecting the environment. We wanted to stay away from gas and coal. Hydrostatic turbines, we present an alternative versus that. And wind and turbines and solar cells are more expensive. So our costs, essentially most of our costs went to the motor. 3D printing was available for free from Tempo, luckily. But just various bits and pieces, but our main cost came from the motor itself. So we came up just over our budget for $581. So what we want to do is improve the data acquisition and include more various meters and other bits into our turbine. We also want to have swap out the motor for a high torque, low RPM motor, and to generate more electricity. And we also must test. We're inconclusive about whether turbo blades will optimize performance. So we want to 3D print regular blades and test that also in a more controlled environment. Questions?
Can I look at your lift and drag coefficient data in the wind tunnel? Next one. Yeah.
It's for turbico blade low and high, as that the force actuator varies. So we took the low and the high to grab an average of it.
I'm surprised you get at high angle at 40, the lift continues to go up. It should start to come down when you go beyond the store angle.
Our advisor pointed that out. However, from the data we acquired from the wind tunnel, this isn't actually what happened.
Like in a wind tunnel, when the angle attack is too large, you have a blocking effect. Because the wind tunnel is not very large. When your angle attack is too large, you block a lot of flow. So anything above 20 degrees angle attack, the results are not accurate. Just keep that in mind. Did you convert your power generation to power coefficient?
We did, and we received about 0.6, I believe. I have to double check.
That's
my
not
data.
possible.
I have to double check my numbers. I'm just trying to recall it off the top of my head. Or we will include it in the final design.
Yeah, try to do the calculation.
What was the, you didn't talk at all today about the electrical design. Say something else about the electrical design.
Well, the electrical design was, well, very simple, and we just wanted a motor to work, essentially, and we also, it was a 3-phase motor that was rated at 10 watts, 10 volts, 60 hertz at 600 RPM, available from manufacturer in China who also made wind turbines. We chose this one because it was, let me get a picture of it. Here's this motor. We chose it because it was available for a very low price as opposed to various other low torque, high torque, low RPM motors, which cost around $1,500. So we chose this one.
How did you measure the power?
The power output came out in 3-phase power, we have a 3-phase to DC rectifier, and we measured the DC voltage and the current coming out of that. Future improvements would be including a more robust electrical system.